The first session consists of 3 talks. So the first speaker is Professor Askar Dzhumadil'daev from the Institute of Mathematics and Mathematical Modeling of Almaty, Kazakhstan. Are you ready, Professor Dzhumadil'daev? Microphone выключен. Please switch your microphone. Оскар, у тебя микрофон выключен. Тебя не слышно.
Слышно?
Окей. Да, теперь да.
Видно доклад?
Yes, you can put your demonstration.
Is it okay?
Yes, but we do not see your demonstration. The title of his talk is Rota-Baxter algebras with non-zero weights.
Okay.
Okay.
Is it
Fine.
okay?
Yes, it's okay.
Perfect. So, let me begin my talk. Suppose that A be an associative commutative algebra of a field K of characteristic 0. A linear operator R that maps A to A is called Baxter with weight lambda if RA times RB is equal to R action RIB plus RAB plus lambda times AB for any AB. Examples: identity. Let ID is identity operator such that ID A is equal to A for any A. And then R is equal to ID is Baxter operator of weight -1. Second example, integration. Suppose that A is a polynomial algebra and the integral A is just usual integration operator. Then integration is Baxter operator with weight 0. Next example, let sequence n A be algebra of sequences of length n with values in algebra A and component-wise multiplication. Let sequence A be all set of all infinite component sequences. Imagine that all components I should be 0 for all I more or less equal to n for some n. And those sequence A by component-wise multiplication and define an operator R by the following rule. So components are particular sums. Then A is Baxter operator of algebra of sequences with weight -1. Next example, Symbiotic algebra. An algebra is called symbiotic if it satisfies the identity AB times C minus A times BC plus CB is equal to 0. Symbiotic algebra and the commutator, your commutator is associative and the commutative. Symbiotic algebra and the Lie commutator A minus satisfy the following identity that we call Qara. So it is identity of degree 4. Products of common radius AB and CD plus product of common radius AD and CB minus common radius Jacobian ABC times D minus Jacobian ADC times B, where a Jacobian is just a Jacobian polynomial. So main subject of our talk is algebra AR. Let R be a linear operator of algebra A, denoted by AR an algebra with vector space A, and denoted by multiplication. A stir B is ARB. Example, if R is Baxter operator with weight 0, then AR circ is Synbiel. R plus is associative commutative. R minus is Rota-Baxter. Another example, let R is derivation operator. Then AR circ is left Novikov. That means first identity means that associator is left symmetric. Second identity means that multiplication operator is right commutative. So here we change BC, but don't change brackets. And Ri minus is Li. And Ri plus, so this is algebra AR with Jordan commutator, is Turtkin. It is very similar to Turtkara. Just difference is here, instead of minus should be plus. And second difference is instead of Jacobian, we have take associator of Jordan commutators. Now, one more example, Non-Baxter algebras. So here we assume that A is not associative commutative. Let A be polynomial algebra, and the multiplication A left triangle, that means DAB, where a D is derivation. Then the integration R equal to integration is Baxter operator with weight 0. In other words, left triangle RB is equal to R A left triangle RB plus RA left triangle B. And the algebra AR, where A sur B is dA integration B, satisfies the following identities. Left symmetric, associator is left symmetric, and it takes place the following identity of degree 4. A circ commutator BC times D, ABD times C, ACD times B is 0 for any ABC. Here, commutator is commutator of multiplication circ. And third identity is slightly complicated. It has 12 terms, and one component should have coefficient 2. And this identity combination of Lie commutators and circ multiplications. Certainly here's mistake. BD should be with circ, A should be with circ, and so on. And from this identity, it follows the following identity, standard identity degree 5. The algebra R5, R minus satisfies identity of degree 5. It is consequence of these three identities. No, we consider associative commutative algebra with linear operator R and denote by RR algebra with the following multiplication. It's clear that AR satisfies right commutative identity. Denote by R minus and R plus the algebra AR and the Lie commutator and the Jordan commutator respectively. Let ABC with usual bracket is associator and denote with a triangle brackets ABC, associator, and the Jordan product. Now let me remind some information about identities. If A is endowed by multiplication star, and F is a non-commutative, non-associative polynomial, then notation F star, A1 and so on, AK, will mean that instead of parameters T1 and Tk, we make substitutions by elements A1 and so on, AK of A, and calculate F A1 and so on, AK in terms of multiplication star. Notation plus star A1 and AK will mean that the element is calculated in terms of Jordan commutator of the multiplication star. Similarly, notation F minus star means that the element is calculated in terms of Lie commutator of the multiplication star. If you use multiplication circ, then we'll write F1 and AK and F plus minus A1 and AK instead of A circ A1 AK and F plus minus circ A1 and AK. For example, triangle bracket ABC is ABC plus or ABC plus with and the circ. In general, the right commutative identity is not unique identity for the algebra AR. Let us give some examples for AR. If R is derivation, then the algebra AR gives AR gives us so-called left-Novick algebra we mentioned above. Right commutative algebra with left symmetric identity of associators. Any Novick algebra and the Lie commutators Lie and the Jordan commutative obtains so-called Röntgen algebra. In our paper, we construct identities of the algebra AR, where A is associative, commutative, and R is a Rota-Baxter operator with non-zero weight. Call for such R, the algebra AR as RB algebra, shortly Rota-Baxter. We construct several identities for RB algebras. Let us define non-commutative, non-associative polynomials corresponding to these identities. The first one is right commutative polynomial mentioned above. The second one is an identity of degree 4, defined by, it is F4, T1 commutative T2, T3 times T4 minus associated T1, T2, T3, T4 plus T1, T3, T2, T4. The identities are COM ABC 0 and F4 ABCD 0 are basic multilinear identities for Rota-Baxter algebras. The identity F4 implies the identity 2, 3. It is notation in my paper. At the end, I'll give some reference. The polynomial corresponding to identity 2 is denoted in my paper is denoted S4 prime. It is a sum of 3 associators. in first place, all arguments are T1, and other three arguments are changed cyclically. And here, we write common data, the 3 first common data. And write commutative, and if the identity of 4, and the lead commutator is third qara. In other words, from these two identities, it follows that it's third qara and the lead commutator. The third polynomial has degree 5 and is defined by the following rule. It's a combination of associators. Note that here, T4, T5 is changed. It's symmetric by T4, T5, and symmetric by T1, T2. And T3 is stable. We show that the identity of 4 implies the identity of third qara and the Ali commutator, and F5 and the Jordan commutator. But the identity of 4 prime doesn't imply the identity of 5 plus. Counterexample gives us the algebra, polynomials algebra, with the multiplication. A star B is a double integral B. It satisfies the identity of 4 prime and the star. But if 5 and the Jordan commutator of star is not identity. For example, if I plus star acted on 1x, x squared, x cubed, and x4, it is the following fraction that is non-zero. And note that F4 prime is also not identity. For example, F4 prime star is acted on 1x, x squared, x cubed is also the following fraction that is non-zero. In Guo, theorem 1117, book, Introduction to Rota-Baxter Algebras. By Rota-Baxter algebra, one understands an algebra with so-called double product, array and RB. We do not know whether the double product algebra satisfies a polynomial identity that doesn't follow from commutative identity. We can check that until degree 5, any polynomial identity of double product algebra with the multiplication integral A, integral B, is a consequence of commutative 1. But it's interesting to consider the following deformation of the double product algebra and the different product. Epsilon A R squared B. If epsilon is 1, lambda is 0, the algebra becomes Saint-Biel. Now let us introduce two polynomials. The following first one is called anti-commutative polynomial, T1, T2 minus T2, T1. Second one is it is commutative polynomial. But note that any algebra with identity com is anti-commutative. And similarly, an algebra with identity A com is opposite commutative. So identities for associative commutative algebra and Baxter operator with non-zero weight. Theorem. Let A be associative commutative algebra over a field of characteristic 0. And R is Rota-Baxter operator with non-zero weight lambda. Then the algebra AR, where new multiplication is given by ARB, satisfy the following identities. Right commutative and identity F4. if A is sequences algebra and R is a partial sums operator, then any identity of the algebra R of degree no more than 4, consequences of the identities are COM and L4. Theorem: the algebra AR and the Lie commutator satisfies third-Kara identity, where Jac ABC is Jacobian and AB is Lie commutator. If A is sequences algebra and R is a partial sums operator, then any multilinear identity of the algebra R minus of degree no more than 4 is a consequence of identities COM and the third-Kara. Next theorem. Oh, here should be identities for. So here I formulate as a lemma. So AR and the Lie commutator satisfy the following identity of degree 5. Here UV, they under these variables UV, they are skew-symmetric. And AB, under two arguments AB, this polynomial is symmetric. If A is sequences algebra and R is a partial operator, sums operator, then any multilinear identity of the algebra R plus of degree no more than 5 is a consequence of identities A COM is 0 and A 5 is 0. So it is repeated 2 times, sorry. So lemma, if A is Baxter algebra with Baxter operator R, then the algebra A satisfies the following identities, where AB with vertical bracket is Lie bracket. So proof, the first one is evident. Let us prove the second one. So if you open brackets, then this one means this one, and for associated it means this one. And if you rewrite this circ operator by operator R, then we have another 6 component sum. And we can present this algebra as A is out of bracket, sum of 3 Q1, Q2, Q3, where Q1 is this one, Q2 is this one, Q3 is this one. And according our conditions, we can rewrite Q1 as follows. Because R is a Baxter operator of 8 lambda. By the same reasons, Q2 is can be written by Baxter parameter. Therefore, if I take sum, I obtain minus Q3 and obtain my identity. Corollary: if A is a Baxter algebra, then algebra AR satisfies the identity XABC, XBCA, XCAB for any ABC. No identities for associative commutative algebra and the Jordan product. Let A be associative commutative algebra with Baxter operator R. Let's define polynomial F ABCUV on A by the following rule. Then ABCUV is equal to minus BACUV. And ABCUV is equal to minus ABCVU. From these two identities, it follows that F5 is identity for algebra AR. Proof is long calculations, but you can check that if you have a Baxter operator with some weight lambda, all weights are cancelled, you obtain these properties. Now, let me give some facts from the proof of multilinear identities of degree 4. In degree 5, they are complicated, and I'm not able to present in my slide. There are two break-things types of skew-symmetric monomials for 4 variables: ABCD and ABCD. In terms of non-planar binary trees, these two types can be constructed by their following trees. So, general form of skew-symmetric polynomial in degree 4 is the sum of the following 15 terms. First 12 can be obtained by permuting of all variables. You use, in the first place, skew-symmetric property. Therefore, permutation should be 12, not 24. And second types of bracketings gives us only 3 non-trivial combinations, non-trivial terms. Therefore, altogether, 15 terms. Aim is to show that any identity of R minus in degree 4 follows from the identity third Qara. To do that, we use realization of Rota-Baxter operator as operator on sequences given by, I mean here, a book of Guo. Introduction to Rota-Baxter algebras. So R means constructs partial sums for these operators, multiplication of sequences component-wise. For us, it's enough to collect relations that give fourth component of operator R. First, second, third, fourth. So for us, important fourth components. If you restrict by first 3 components, you don't obtain enough number of information. For us, it's enough to collect relations that give fourth components of operator R. Below, we use notation of the form A0101 instead of 01010000. We omit 0 terms, last 0 terms. And X4 core minus, the element of R minus, calculate in terms of Lee reader. For example, if A is the following sequence, B is the following sequence, C is the following sequence, then first 2 components of this polynomial vanishes. And third component is this one. But we pay attention for first component. It gives us this one. So it's a combination of 15 terms with integer coefficients. In the table below, we give 12 relations that give fourth components of X4 core minus ABCD, where A is equal 0101, and sequences BCD are as follows. So here we obtain 15 term. So we have 15 a relation with 15 terms. And here we consider different kinds of different versions for ABC, BCD. It is another 5-1. And finally, our last 3-1 gives us this one. And if you solve these equations, we obtain a linear system of 12 equations with 15 unknowns, lambda I. This system has rank 12, and unknowns lambda 1, lambda 2, lambda 4 can be selected as a free parameters. And the solution of the system is the following. And we substitute in our polynomial these presentations of coefficients lambda by lambda 1, lambda 2, lambda 4, and obtain the following form for X4 com, where G1 is the following polynomial, G2 is the following polynomial, and G3 is the following polynomial. And the direct calculations show that it's not so difficult. So G1 is exactly third qara, but with arguments CADB. G2 is third qara minus third qara, but arguments ACBD, BADC. And G3 ABCD is BADC. So any multilinear identity of degree 4 of the algebra R minus, where R is Baxter operator, is a consequence of the identity to qara. Now let me consider algebras with other multiplications. Let M epsilon AB is A double integral B plus integral A integral B. And ABC epsilon is the following associative. It's easy to check that Jordan common rate of M1 and the multiplication M1 can be calculated by the following formula. It is fraction. Degree is xi plus j plus 2. And here, a plus j plus 3 and a plus j plus 4. And on denominator is a plus 1, a plus 2, and j plus 1, j plus 2. And if you substitute here, you obtain that ABC is 0 when epsilon is 1. Now we construct an algebra with multiplication EI, EJ, epsilon IJ times EA. Let M be matrix whose components are indexed by elements of some subset I, subsets of integers, such that epsilon ij is 0 if A no more than j, and epsilon 0 if A is more than j. Let for simplicity, A, j are elements of fields. Then algebra A depends from index set of indices I and M is algebra with base EI and multiplication EI circ AJ is epsilon IJ AG. Since EIAJ times ES is epsilon IJ EI times ES is product of EIJ, epsilon IJ and epsilon IS EI. Similarly, EI circ ES cert Ej is epsilon is Ei times Ej is epsilon is Eij. We see that the our algebra is right commutative. Now, let's check that it satisfies the identity of 4. So we have, it is not so difficult to calculate that. So first term of the polynomial of 4, Ai times commutator Ajes times Ek is equal to Ei with the following difference of 3 products. هذا Ei Ek also not so difficult to calculate that it is sum of so coefficient is difference of 3 products of components of matrix M, and here PS Ei. Similarly, Ei as Ej Ek, here we change S and J is equal to this one. And we have, if you add, we have that this is Gijsk, Vijksk is sum of 6 triples. We have to establish that this polynomial is 0 for any Ijsk. Since the polynomial Gijsk plus Gijsk is 0, it's enough to do that for the case when J is no more than S. Might be the following 3 cases. If I is less than J, then epsilon Ij and epsilon S is 0 by definition. Case 2, let J is no more than I, no more than S. Then epsilon Js, epsilon is 0. Therefore, all of, so we consider here, so 6 terms. We consider each terms. Then we see that each terms are 0. Case 3, J is less than S less than I. Then epsilon Js is 0, epsilon S is 0. And we have the following, I remind the following properties of the matrix M. And if we calculate these 6 terms, we obtain that this is 0. And other 2 terms are non-trivial, but they cancel to each other. And we see that in all cases, Gijsk is 0. So we establish that F4 is identity for algebra AIM. Now let us consider Lie and Jordan commutative of the algebra AIM. We see that Ei times Ei is 0, Ej is times Ej, Jordan commutative is also 0. And commutative Ei times Ej is plus minus epsilon index minimum Ij and times E maximum Ij. And for Jordan commutator, epsilon I, epsilon j is epsilon minimum Ij, E maximum Ij, if I is not j. More exactly, we see the following rules. And if I is equal to z and epsilon j is non-zero for any j, then we see that this algebra coincides with derivatives, second derivatives, and the circ and the commutator and the Jordan commutator. On the other hand, for any S, a subspace JS spanned by AI when I is no less than S generates an ideal of AIM. That is a linear span of base elements AI when I is more than S. Since JEI is 0 if I is J, and JEI is element of linear span of E maximum IJ, and maximum IJ is more than S, hence the algebras are not solvable, are not nilpotent, and you create a chain of ideals. And now consider recombinations of symbiote products. Now let me introduce new multiplication, ABN, is the following. In I, minimal coefficient, times 1 minus 2in, and here integral I, A, n minus a double integral b. So integral IA is, here integrals are repeated I times. For example, AB2 is A double integral B minus double integral A times B. X3, X4, index 3 is the following one. Suppose that let A circ 2B is A integral B plus A integral double B, and H3B is integral A double integral B plus A triple integral B, and R4B is double integral A B to A triple integral B plus A for repeated integral B. Then we see that if a prime is identity for multiplications A circ 2B, A3B, and A4B. But if 4 is identity only the multiplication A circ 2. Moreover, the multiplication A circ 2 satisfies left symbiote identity. So these examples gives us that these identities F4, F4 prime, F5 plus, and so on, they are non-trivial identities. They are independent for each other. Now consider one more multiplication. A star 0n is a sum of I begin from 0 and n, binomial coefficient in I repeated integral A, n minus I repeated integral B is associative. So it can be proved easily by induction. If for n is 1, it is well known, it is Loday's result. So that multiplication is star 0n is associative. We have checked that this is homomorphism. So it is not so difficult. So we can check that this is really homomorphism. And from here, it follows that if it is associative, then it should be also associative. So this one is generalization of Loday's result. The multiplication A star 1 and B. So here in I, integral I repeated I times A, integral n minus I plus 1 repeated times B. And moreover, we define A star Kn by the following rule. And we prove the following properties of the multiplication A star index Knb. A0n is associative and commutative. Star 1n is not associative, non-commutative, but it is left symbiote. Star 2n is not left symbiote, doesn't satisfy the identity of 4, but it satisfy the identity is right commutative and F4 prime. Hence, this gives us one more example of third-order algebra. And the star Kn is right commutative if K is more than 2. Therefore, multiplications star 0n satisfy identities. Right commutative if 4 is 0, if 4 prime is 0, third order minus is 0, and if 5 plus is 0. Their multiplication star to n satisfy identities. Right commutative is 0, if a prime is 0, and third order minus is 0. But then satisfy identities if 4 is 0, if 5 plus is 0. No, right commutative property of star Kn can be proved easily. If I take EI is the following divided power polynomial, then for any ij no less than k plus n, s is any no less than 0, integral s repeated integral s times EI is a plus s, and EI times EJ is I plus j minus 2n minus 2k, I minus n minus k, a plus j minus k minus n. Therefore, for any ij at least n plus k, this one is the following polynomial, with the binomial coefficient is this one. Therefore, the identity algebra with degree 4 is 4 types algebra. No, finally, we have to consider the multiplication A diamond B is dA integral B. I remind that it is Novikov-Baxter algebra. Then it satisfies, it is right symmetric. It's easy to check. And it satisfies this identity S13 when first component is stable, other components are changed by 6 variables. So it is also not so difficult to check. And let me give references. Novikov algebras first appeared in paper Novikov and Balinsky for some brackets of hydronumeric type. And associativity of Senbiel product and the Jordan Komorida is appeared here. Lodey product for Leibniz cohomology and your Leibniz algebras. And good book on Rota-Baxter algebra is Go's book, An Introduction to Rota-Baxter algebra. And Baxter operator was appeared first in the following paper, analytic problem whose solution follows from a simple algebraic identity. And it was popularized, and he did a lot of new achievements by Rota-Baxter algebras and the commutative identities into papers in Bulletin American Non-Society. And Novikov Jordan algebra, third algebras appeared in my paper, this one. Third algebra appears in my paper in Senbiel algebras and the commutator. And I mentioned that this talk was first done in 2016 in Sofia in the International Conference Groups and Rings Theory and Applications. But it seemed that nobody noted this paper. When I was recent in Oberwolfach, I met Professor Guo, and I told these identities. He mentioned that these identities are new. Therefore, I decided to take a talk in seminar of European non-associative algebras. So thank you.
Thank you very much, Professor Dzhumadil'daev. So very interesting, but very complicated calculations. So I have a question. All algebras are considered over the field of characteristic 0, yes?
Right.
Because if positive characteristics, the calculation should be more complicated.
because of integration.
Yes. Thank you. Please, questions or comments? If no questions, let's thank Professor Dzhumadil'daev for a very interesting talk. Thank you very much.
Thank you.
Now we have 10 minutes break and start in 10 minutes. Thank you. The next talk by Veselin Drensky from Bulgaria, the Specht problem for varieties in Z sub n graded Lie algebras in positive characteristics. Thank you. See you in 10 minutes.